So in this question, the conduction rate through the two materials must be equal. If they were not, the temperature in the material would be changing. So call the temperature at the boundary between material 1 and material 2 T sub x. Therefore, we're going to have Q over T equal to K1 times the area times temperature in the first area minus temperature at the boundary divided by the thickness, L1. And we're also going to have that be equal to K2 times the area, it's the same in both cases, times T of x minus T2 divided by L2. Okay, so this then means that, we'll write it here, that Q over T multiplied by L1 divided by K1 times A is equal to T1 minus Tx, or you can also write Q over T, not T2, Tx, Q over T times L2 divided by K2 times the area is equal to Tx minus T2. So add these two together and then solve for the heat conduction rate, okay? And we're going to do this on this new page. That's going to give us, well, Q over T is constant for both, as well as 1 over the area. So we're going to pull both of those out front. And then multiply that by, you have L1 over K1 plus L2 over K2 is equal to T1 minus Tx plus T1 plus Tx. Or excuse me, plus Tx minus T2. Well, the Tx's are obviously going to cancel here. So this is equal to T1 minus T2. Solving for Q over T, we find that this is equal to the area times the ratio of T1 minus T2 to L1 over K1 plus L2 over K2, which is equal to the area, times T1 minus T2 divided by R1 plus R2, because R1 is defined as L1 over K1 and R2 is defined as L2 over K2. So this is R1 plus R2. Okay, so the R value for the brick needs to be calculated. So using the definition of R given on page 402 of the textbook, we find that R is equal to, of course, L over K, as we had just mentioned. So in this case, it's going to be equal to, we're going to have 4 inches. This is the numerator. And then convert that into feet using the fact that there are 12 inches in a foot. So this would be multiplied by foot divided by 12 inches. So now our numerator is in feet. And in the denominator, we have 0.85 for K, which has units of joules per second times meter times degrees Celsius. Okay, but let's get it out of seconds and into hours, out of meters and into BTU, and or out of joules and into BTU, and out of degrees Celsius into degrees Fahrenheit. So 1 BTU, so we'll multiply this by the first conversion. 1 BTU is equal to 1,055 joules. So 1,055 joules. So now we're in BTU, which is good. Okay, so now let's convert to feet from meters. So, of course, 1 meter is equal to 3.281 feet. Feet, so FT. Okay, and now let's convert Celsius into Fahrenheit. So we have 5/9 degrees Celsius is equal to 1 degree Fahrenheit. So we have 5/9 degrees Celsius to degrees Fahrenheit. Okay. And then, of course, now let's get into hours from seconds. So we have 3,600 seconds for 1 hour. So carrying out this calculation, this comes out to equal 0.69. And the units here are feet squared times hours times degrees Fahrenheit divided by BTU. Okay, so now that we know that, we can go ahead and finish this. Thus, we have a value of Q over T which is equal to the area times T1 minus T2 divided by R1 plus R2. Okay, well, we were given here on the first page R2. We know the area, and we also know T1 minus T2. And what we had just calculated was R1. So this is R1 is equal to L1 over K1. So plugging in the value we just calculated for R1, the value we know for R2, the value of T1 minus T2, and the value of the area, we find that this is equal to 350 BTU per hour, H. And we can box that in as our solution to the question.